We said nice things about it was that it's simple, it's compact, it's efficient, and it's very easy to spell. The cons of it are, in fact, maybe I should have listed these in the other order. Here it says, we'll say there's sort of a restricted class of motions defined by the linear model. The linear thing we can get around by using what's called an extended Kalman filter. A much bigger problem is it's got this nice unimodal distribution assumption. You're assuming the world really is a nice Gaussian of some uncertainty. And the question arises, what would you do if things are not a Gaussian? So what's an example of when you might need a non-Gaussian situation? Well, you remember these videos? Okay, and again, this comes from the Izard and Blake condensation tracking paper. There's all sorts of dynamics going on here of things jumping around. Let's see if I do that again. Yeah, there she goes. And things move quickly. They may be able to be nice and smooth sometimes. Then something rapid will happen. So like when the leaves are blowing in the wind, for a while they blow nicely. But basically, the problem here is that things are moving smoothly, and then all of a sudden you'll get a perturbation. And you'd like to be able to keep track of that. So graphically, we're going to show that like this, okay? So now we have the same model that we had before, okay? We have an estimate from the last time. We have a deterministic shift. We apply some smoothing because we grow the uncertainty, and then we take our measurement and we update our estimate. But now these are not Gaussian lumps, right? These are sort of arbitrary distributions. And in fact, this particular figure is taken from the paper that introduced the particle filtering that we'll talk about in a minute to computer vision, that condensation paper I just mentioned. Before we go any further, just something you should know. In particle filtering, the measurements are typically referred to as the z's, z sub t, and not as y of t. It was just the way it was done. It has to do with whether you're connected to vision or robotics. In order so that it aligns with various papers and other formulations you'll see, we're going to start showing z's in the slides to come. It also made it much easier to borrow slides from other people because they were using the z's. All right, so the key to sort of particle filtering is the following. If we have a distribution, and here we have a nice little distribution, which you see is, I don't know what that distribution is, but I know one thing. It's not Gaussian. Now, somebody who's really smart out there might say, well, it looks to me like a mixture of Gaussians.
Well, it sort of looks to me like a mixture of Gaussians.
Yeah, in this particular case, maybe it is. That's just for convenience of drawing. And in fact, there is a relationship between mixtures of Gaussians and particle filters, which we won't even talk about. But basically, the idea is you have a bunch of things which together represent your density. In particle filters, or sample-based methods, what you have is you have a set of particles. And here the particles are drawn out where you can see these particles. It says xt. That means these happen to be our particles at time t. And there's n of them, and the bigger n is the better. And you'll notice it says weighted here in parentheses, because sometimes they're weighted or sometimes they all have the same weight. The density is represented by sort of where the particles are. So you see we have a nice high density here. So we got lots and lots of particles there. Okay? Not so many particles here, not so many here, and lots of them there. All right? So that's where they are. And if they were weighted, it would be as if you can think of that as having two particles in the same spot. If I had double the weight, it would be like having two particles at the same spot. And now you can say that the probability density that x is some value is essentially the probability, if you were to draw out a particle, that you would get a particle whose value is really, really close to that spot. Okay, and that's what it means to use samples or particles to represent a particular density. And if you're doing that, then your overall goal is you want, sort of as n gets bigger, the idea is that the probability of getting a point from this distribution, that's x as an element of xt, is approximately what the underlying probability was. And for tracking, the idea is given everything we've observed so far. So what are our observations? Remember, they're z's. So given everything that we've observed so far, what's our belief about where x is? And we want to end up with a set of particles that gives us that density. We still have to do the same things we had before. So you remember when we're doing tracking, we had this notion of a dynamics model. For Kalman, it was a linear model. So the idea is that at each time step, we have some prediction that allows us to say, well, if I have some density about where I think I am, what's my new density? And in that particular case, it had to be linear in order to make the math work out. That was, the underlying part of the Kalman. All right? But in general, we can have a more general state transition matrix, right? So the idea is that what is the expected change from time t to t plus 1? Okay, so if I'm at some point, or if I'm guessing that I'm at some point, I could say, what's my expected change? So what's important about this, and the reason I'm going on and on about this, is besides just having sort of a dynamics model that says how things are likely to evolve, I can also include a notion of perturbation or control. All right? So the perturbation means if I was here, maybe I know that I took 2 steps to the right. Now Megan's freaking out again. All right, I'm back. All right? So what I would do is I would say that, okay, the expected state transition is that I take where I am, I take 2 steps to the right, and then I add some noise. So it's a little bit like, remember we talked about that in the linear model? I could actually have a different linear transition at every time t, but usually we keep them constant. Here, we're going to have the notion of an input, and the input is represented as u. U for input. Don't ask me. If you want to know why, ask some control theory professor, because they always use u as the inputs or as the desired. Anyway, so we're going to see a u sub t. That's the control or the input or the perturbation that got added to the system at time t. And we assume that we know that. All right? So what we've done is we've changed our filtering just a little bit so that besides just taking observations, we're going to assume we have observations plus assume that we have we know what the inputs are. All right? Lots of words, but I hope you follow that.
Now, why would you want to add perturbations to a model? Isn't that what noise is for? Let's consider a real-life scenario. Let's say I am a robot ambling away on the moon. My goal is to reach this flag. I can use my camera to detect and track the flag. This is what my view of the world looks like. Now, where the flag shows up in my view and how it moves depends on a bunch of different things. For instance, my movement across the surface, both back and forth and turns. Now, the surface is really bumpy. This can cause my view to shake quite a bit. I can also move my camera independently, pan, and tilt. The most annoying is probably the wind blowing the flag all over. It really messes up the appearance. So which of these are known perturbations that we can model for? Okay, this was fairly easy. When we're moving, we know how we're moving. That is, we know how our view of the world should change with the movement. Therefore, we can take it into account in our model. Same goes with turning the camera. Now, perturbations caused by the terrain or wind are things that we cannot explicitly model for. We still know that they can affect what we see, so it's probably a good idea to include it in our noise model. Known perturbations, or control inputs or actions, allow us to build in phenomena that we can explicitly model for.
So we're going to go over a Bayes filter framework, and so given 4 things. First is, I'm going to need some prior belief about where I'm starting. Okay, so that's P of x. Where did that come from? Again, remember that drive up to Delphi and asking the oracle and all that stuff? So you forgot your luggage, so you went back to Delphi, you got another prior, and it tells you how things are starting. But again, maybe with a large uncertainty. So here we have our dynamical system model, and so it's the probability of some new x given my belief about the previous x plus this input. By the way, you see here it says u sub t minus 1. The world is sometimes schizophrenic about whether you think of the input as happening just after the last measurement, so it was u at t minus 1, or u happened now and I want to estimate what the state is now. So whether it's ut or ut minus 1, it's whatever you're going to add on to xt minus 1 in order to make your prediction about xt. All right? So we're given these 2 things. We're given a prior and action model. We're also given a sensor model. And this is going to be really important, a little bit important this lesson, very important next lesson. And the sensor model is our likelihood, okay? And it is not, I'm going to tell you what it isn't first. It is not given some sensor reading where do I think the object is. You might think that's what it is, but then you would be thinking incorrectly. No. A likelihood model is, if the object were really someplace, what's the likelihood of my measurement? So normally what you'll see is, and we're going to see some later, like a little Gaussian blob drawn over the place where the measurement was. That does not mean, okay, that given this measurement, this is my distribution of where things are. No, no, no. What it means is, this is my likelihood, so it's highest if x was actually at this point, and then it falls off slowly. All right? That's the likelihood. And then finally, we're given the stream of observations, the z's, so z1 through zt minus 1, or through zt. And also, we know the actions, okay? So we know the action data u1 through t minus 1, okay? So those are the four things that we have, all right? What do we want? Well, what we want is the estimate of x at time t. Okay? Same thing we've always wanted since we were little children. And in the Bayesian world, this is called the belief or the posterior of the state, right? And so sometimes it's even written like this, BEL, for belief of xt. What's my belief about xt given everything that I've observed so far, knowing all the perturbations, and given my current measurement?
I'm still a little fuzzy on this likelihood thing. Let's jump back to the moon. Did I tell you about my star sensor? I use it to navigate around. There are hardly any other landmarks. When I point it to a region in the sky, it says bright star. That is, if there is a bright star in that region. If I told you that I was looking at this particular region in the sky, how likely is it that my star sensor would go off and say bright star? Choose the appropriate radio button underneath on a 3-point scale, from least to most likely. Now do the same for these other regions in the sky. Remember that I'm asking you to estimate the likelihood P of bright star given the sky region. Okay, the first one is very likely. Second and third, not so much. Last one, maybe. Okay, so the distribution of P bright star given sky region looks something like this. Remember that this is not enough to give me a definitive answer of which region I'm looking at. I need to combine this with my prior probability of where I think I'm looking. This would come from my previous estimation step or just be a random distribution in the beginning.
A couple of more things about the model that are similar to what we did before for the Kalman, okay? Since I know some of you have a machine learning background a little bit, drawn here is a graphical model. The idea is that x is only impacted by what the x was before and what the new perturbation is, and the z's, the measurements, are only a function of the current state, all right? And that's written in the following way, right? The first thing says the probability of the measurement, given all the states, given all my history, is only a function of the current state, and that's sometimes called sensor independence. Okay, the sensing is only dependent on the current state. All right. The other element is this one that says the probability of the next state, given all of these things that came in and including the states before, is only a function of where we were before plus the current input. And by the way, here, this is written as ut, not the ut minus 1. That's what I was telling you about before. It's shame on me because I did both of these and I should have made them consistent. But the idea, this is the Markovian property, right? We had the Markovian property last time also. The Markovian property says if I know the state at the last time, none of the earlier state information, none of the earlier measurements, none of the earlier anything matter except the state then, and then the one thing we've added new this time is action at the current time, okay? That's the Markovian property. So before we go further, I'll just remind you again of Bayes' rule. We looked at this last time. The straight Bayes' rule is that we can say that P of x given z, the P of the state given the measurement, can be written this way. This is the likelihood, all right? This is the total probability of z. That's our prior before the measurement. That's our belief, if you will, of what the value was, okay? So what's important here to realize is